Imagine standing on solid ground, and suddenly, the earth beneath your feet gives way. No, this isn't a scene from a disaster movie. It actually happens more often than you think, often silently. Hidden beneath our cities, you use sidewalks, roads, and buildings every day. But you've probably never considered the invisible rivers flowing below. In 2015, a construction worker in British Columbia narrowly escaped disaster when the ground beneath a steel caisson collapsed. The culprit, groundwater, quiet, and seen, and deceptively powerful. It's easy to forget that the ground we walk on isn't always solid. Beneath the surface, water carves paths and applies forces that can make entire structures fail if ignored. Today, we're going to explore how groundwater moves, why it's one of the most overlooked challenges in engineering, and the clever ways modern design fights this hidden enemy. Stick around to see the invisible battles that keep our dams, foundations, and even temporary construction sites safe. And comment if you've ever wondered why the ground beneath your feet might not be as stable as you think. The hidden problem beneath the surface: groundwater is peculiar because it's mostly invisible, yet it can behave in ways that defy intuition, and like rivers or lakes, you can't just look at it and understand its flow. It's hidden, confined within soil, sand, and rock, quietly exerting pressure on whatever sits above it. One of the most dramatic examples of groundwater's power comes from dam engineering. Dams are designed to resist the enormous forces of water pressing against them. Hydrostatic pressure, the weight of water pushing on a dam, is relatively straightforward to calculate, even for early engineers. But beneath a dam, water doesn't just sit still. It flows, often through tiny cracks and pores in the soil, generating what engineers call uplift pressure. Think about it: a massive concrete dam relies on its weight to stay in place. Now imagine that water below the dam is literally pushing upward, counteracting the dam's own weight. Neglect this force, and even a carefully designed dam can slide, tilt, or fail entirely. This isn't hypothetical. In 1928, the St. Francis Dam in California collapsed catastrophically due to uplift pressure and other engineering oversights, killing over 400 people. Groundwater doesn't only threaten dams. It complicates almost every structure built below the surface, retaining walls, basements, tunnels, and temporary constructions like caissons. These watertight chambers are used to hold back soil during construction, but if groundwater is underestimated, the soil itself can turn into a liquefied trap. One misstep, and a worker could be pulled into a sinkhole in seconds, as nearly happened in British Columbia. So how do engineers even begin to predict something as elusive as groundwater? The tool of choice is something called a flow net. This graphical technique divides the subsurface into a grid, showing both water pressure and flow directions. It's like mapping invisible currents in the soil, except the currents can change depending on soil type, structure geometry, and even tiny variations in water levels. Engineers also use cutoff walls to manage groundwater under large structures. By inserting a barrier into the soil, they can lengthen the flow path and reduce the pressure acting on a foundation. It's simple in concept but tricky in practice. If a cutoff wall doesn't reach a solid impermeable layer, some water still sneaks underneath, but the reduction in pressure can make the difference between stability and collapse. Another method is drainage systems. Engineers design drains beneath structures to filter and redirect groundwater. These drains relieve the pressure while preventing soil particles from washing away, a process known as piping. In effect, drains act like invisible safety valves, controlling the hidden forces that could otherwise undermine a foundation. To visualize this, picture a caisson being dewatered. Pumps draw water out from the surrounding soil, creating a dry work area. But even minor errors in this process can cause the soil outside the caisson to become unstable, leading to the ground literally boiling up. The hydraulic gradients created by dewatering control both the speed and the direction of subsurface water flow, meaning that one miscalculation could turn stable soil into a rapid, destructive flow. The hidden challenge of groundwater is that small differences in design, soil permeability, and water level can have dramatic consequences. Every dam, wall, or excavation must account for these invisible rivers, or risk catastrophic failure. It's a constant battle between nature's quiet forces and human engineering.
So how do engineers win this battle? One of the most fascinating strategies is the combination of cutoff walls and drainage systems. That's addressing different aspects of groundwater. Cutoff walls lengthen the path water must take, reducing pressure rate. Drains relieve pressure and filter the soil to prevent erosion. Together, they stabilize massive structures without anyone ever noticing. The logic behind these solutions is surprisingly elegant. Darcy's law, a principle in fluid mechanics, shows that groundwater velocity is proportional to the hydraulic gradient, essentially how steeply pressure changes across a distance. We increasing the length of the flow path with a walk or providing a controlled outlet through the drain. Engineers manipulate this gradient, coming water that would otherwise destabilize the structure, but the ingenuity does not stop there. In more extreme cases, the root curtains are injected beneath them. Heat pressure growth fills cracks and voids in the soil, creating an impermeable barrier. In effect, engineers can stop the subsurface to redirect water where it won't cause harm. It is a form of invisible artistry, designing forces you can tissel to protect structures you can. Temporary structures, like caissons and retaining walls, use similar principles. Wall points mount, even these patched walls weight pumps lower the surrounding water table, preventing soil from flowing into the work zone. In deeper or more sensitive soils, engineers make drive-shaped pillars or deep trenches to reach impermeable layers. Every action is about controlling what the AI cannot say, crafting stability from the invisible. WHTS remarkable is how these solutions evolved over time. Early engineers often underestimated groundwater as power, leading to failures. But modern civil engineering has transformed these invisible forces from a hidden hazard into a predictable element of the system. Today, computer simulations, flow network, and careful field measurement allow engineers to anticipate problems before a survival event hits the ground. Consider this. The next time you walk past Adam, stand on a bridge, or pass a construction site, look at the ground beneath is a lightweight movement. Invisible pressures, hidden currents, and carefully engineered barriers are constantly at work to keep the world above surface. The state, concrete, and soil user are only part of the story. The real hero is the hidden logic beneath. And here is a question to think about. What would you do if you realize that every building you enter relies on engineers controlling forces you can't see? You may never look at a city Adam, or a basement the same way again. That is the beauty of the system. It is a mix of science, art, and forensic, all hidden in plain sight. Groundwater is invisible, unpredictable, and powerful. Yet, through clever engineering, we can turn it, redirect it. Can to see it our advantage without ever noticing. Dams, caissons, retaining wall, they all rely on understanding the bizarre parts of water beneath our feet. Next time you step onto solid ground, take a moment to think about the hidden forces at play and the brilliant basics keeping everything stable. If you learned something new today, comment below with which structure surprised you most. And subscribe to see more hidden logic behind the world we take it for granted. Once you start noticing these invisible forces, you will never see everyday structures the same way again.